So across my periodic table, I have trends in electronegativity. I can not just, I don't need to look up the electronegativity of every single element. Like I said, fluorine is the most electronegative. But there is a trend that I can work this out. Even without knowing the exact value, I can usually work out if a molecule is going to be polar or non-polar based on the combination of where they are relative to each other in the periodic table because of the trends. So here they are. The trends in the periodic table is that going across a period, my electronegativity increases. Electronegativity increases across a period. Why? Well, let's take our second period again. So across this first period of the periodic table, my electronegativity increases. How much it wants electrons increases. And that makes sense based on what we said earlier about my lithium and my beryllium. They wanted to lose their electrons. So if they want to lose electrons to become stable, they certainly don't want to gain them, which is like electronegativity, how much it wants to pull electrons towards itself. So these ones, yeah, that would make sense that they're low. But as we go further this way, it would make sense that my fluorine, its electronegativity increases because it really, really wants that electron. It's close to the 10. Oh, one of the things I should say is that my noble gases are kind of exempt. I don't have high electronegativity at all because they don't want to gain any more electrons. So I'm drawing a little barrier here. So electronegativity increases across a period, but not up to the point of the noble gases. They don't want electrons. So my fluorine has the highest electronegativity. How is this related to the size of the elements? Well, one of the things is I try to think kind of visually, and one of the ways that I imagine this trend is that what's happening as I go across is that my elements are getting smaller and smaller and smaller. So across a period, across a row of the periodic table, the elements get smaller and smaller and smaller. Now, that might not seem obvious, especially considering the atomic number is increasing 3, 4, 5, 6, 7, 8, 9. So it's getting a bigger nucleus, and yet the whole thing is getting smaller. And the reason for this is because that positive charge in the nucleus is pulling in the negative charge of the electrons on the outside. So as my nucleus expands and gets bigger, then my electrons around the outside are pulled closer and closer in. And that's what's happening here. Every time I add an extra proton, my electrons are pulled a little bit closer. The opposites attract, negative and positive charges. So adding an extra proton pulls in my electrons just a little bit. And then adding an extra proton pulls it in a little bit and a little bit and a little bit. Now, across a period, that's quite a significant difference in size, but it is a trend. One step, then the next, then the next, just a little bit more. Every time you add an extra proton, my nucleus is pulled in a little bit more. And the smaller an element is, then the more electronegative it's going to be. It really wants to pull and hold in those electrons really, really tight. So electronegative, how much it wants, it's really holding on very, very tight to those electrons. So my small ones are the ones that really, really want to hold on to the electrons. So electronegativity increases across a period because my size decreases. There's another trend. As I go down a group of the periodic table, my electronegativity decreases. Electronegativity decreases down a group. So increases across a period, but decreases down. Now we know it increases, like I said, because it's adding extra protons each time, and that protons pull in the electrons closer and closer to the nucleus. But why does it decrease going down a group? Especially considering if I look that my number of protons is increasing um, by quite a large amount as I go down a group. My first group of elements here, my lithium with its 3 protons goes to sodium with 11, potassium 19, rubidium 37. So you would have thought, based on the logic of before, my nucleus is increasing by quite a bit. Does that not pull everything in closer? And yet my bigger nucleus is pulling in those electrons, the opposite attract still matters. But something else is happening as I go down a group. As you go down a group of the periodic table, you're adding an extra layer. Remember what I said about that bus rule, is that only 2 seats on that first row. And then as I go up stairs on the bus, and they're filling in their seats, and then that gets filled, and I need to add another layer, and then that gets filled, and I need to add another layer, and so on and so on. It needs to get bigger and bigger and bigger. And even though my nucleus is getting bigger as I go down, I'm adding an extra layer for every new element. So it increases in size much bigger, much faster than it is sort of contracting based on the nucleus getting bigger. Let me show you what I mean. So the idea is my lithium has 2 layers. So 2 electrons and a third one like this. So 2 layers. My sodium is going to have 3 layers. So 1, 2, 3. My potassium is going to have 4. 1, 2, 3, 4. My rubidium is going to be 5. 1, 2, 3, 4, 5. And I'm already going off the page just with these first 5. So they're getting bigger and bigger and bigger every time I add an extra layer of electrons. And of course, the bigger it is, then, well, like I said, it's, the smaller they are, the more electronegative. They're really holding on to their electrons. But as I get bigger, they care a lot less about the electrons. So like my rubidium here, is that my positive charge in the middle, my nucleus, my very, very small nucleus relative to the size of the whole thing, is not really too interested in the electrons on the outside that are now a huge distance relatively away from that positive charge. So there's not much holding this all together, keeping them held tight. So it just doesn't have a very strong electronegativity, a want for these electrons holding them in. So the bigger the element is, the less electronegativity. Electronegativity decreases always down a group because they're getting bigger and bigger. I'm adding an extra layer. I always know how many layers of electrons it is by just counting how many periods it has as well. So I know that my rubidium has 5 because it's 5 down. So based on these two trends, electronegativity increasing across a period and decreasing going down a group, it means that I don't always need to look up the electronegativity values of elements to know what combination of them would be polar or non-polar. Instead, I just, see where they are relative to each other in the periodic table. For instance, if I had something like an oxygen bonded to another oxygen, well, their difference in electronegativity is nothing. My oxygen is going to have the exact same electronegativity as another oxygen. So when they come to have their covalent bond, and actually they have two, a double bond, is that this molecule here is going to be totally non-polar. Non-polar. Non-polar because there's no difference in electronegativity. The electrons that make up the bonds are being shared totally equally, nice and even. No one is pulling more than the other. In the tug of war of who wants these electrons more, if it's the same element, then, well, they want it equally. So no one's going to win that tug of war. So non-polar. I don't have different poles. Let's contrast that to something like hydrogen bromide. So my hydrogen bromide, my difference in electronegativity here. So my bromine much further to this side, my hydrogen over there, which has a relatively low electronegativity. My hydrogen has its 1 electron and wants to try and get the 2. My bromine has its 7. So yeah, they're going to form a nice bond here to link them together. That takes bromine up to the 8, takes the hydrogen up to its 2 that it wants. So they're going to form a nice bond, a sharing of electrons. But the bromine wants it more. I could tell because it's much further to the right side of the periodic table where they really, really want electrons. It's in group 7, so it's 1 away from 8. So its electronegativity is going to be much higher than the fluorine. So in this link, my electrons are going to be much closer to the bromine than the hydrogen. It gets this delta negative, gets this delta positive, and therefore, if I imagine it as a globe, this molecule, I have a negative pole, a positive pole, a polar molecule. So as for our trends in periodic table, our electronegativity is related to the size of it. And all this comes together of how much it wants electrons. It all wants to be stable, like one of these nice noble gases on this side of it. So across the periodic table, going from left to right, going across a row, a period, is my electronegativity increases. Why? Because the elements are getting smaller. It's pulling those electrons in closer. Every time I add an extra proton, my electrons are pulled closer and closer and closer towards the nucleus. So it's decreasing in size across a period because that increase in the number of protons pulls everything in a little bit closer. And as I go down a group of the periodic table, I'm adding extra layers. And by adding extra layers, it's going to get very big, very fast. So down a group, I'm adding layers of electrons. So they're filling a complete shell of electrons in that energy level. So it means that it needs to add an extra one. So every time it gets to 8 on this side, I filled a complete shell, so to add any more, oh, I need to go to another row. And then I get to 8, and oh, I need to add another row. And then I go across on 8, need to add another row. So it's getting bigger and bigger and bigger. And that huge expansion means its electronegativity decreases. So the trend is as the size, my atomic radius, how big the thing is increasing as I go down, and its electronegativity is decreasing. How much it wants electrons is getting less and less the bigger it is. Okay, so hopefully that's helped you out a little bit about trends in the periodic table. We touched on lots of different things there. We talked about ions, we talked about polarity, a little bit about bonding as well. And it all comes together. I think one of the things that's really brilliant about the periodic table is that the more we understand about chemistry, the more bits fit together. It's not like separate subjects. Chemistry is more like a jigsaw puzzle. We've got to fit all the pieces together, and the more pieces we have, the picture starts to look a little bit better. So this periodic table was a gift that one of my students gave to me. They said, oh, I've got one of these and it's really useful, just a nice sort of periodic table, piece of paper that you could just have with you, keep it in your bag at all times. It's very useful. And I said, oh, thank you very much. And then after I said thank you, the first thing I said was, oh, there's a mistake in it. So there is a mistake in this periodic table. I know it's quite small in the screen, but if you would like to pause the video, perhaps you can figure out where that mistake is and let me know in the comments. Can you see the mistake in this periodic table? All right, let me know in the comments. And if there's any other topics you want me to cover in chemistry, then again, put it in the comments, let me know. I'm grateful for all feedback, even negative feedback helps boost the algorithm. So make sure to bash that like button and subscribe if you want to find more lessons in chemistry. All right, thanks for watching. Your time, your patience, and attention. See you later.